Okay, let's get started, everyone. So we're discussing the illumination cone. I think that, correct me if I'm wrong, but we covered pretty much everything, right? With regard to illumination cone, and we saw the two-dimensional example, right? And the algorithm, right, that you can implement in probably, I'm gonna make a guess here, 5 minutes. All right, maybe 10, right? It's simply stated, take the images that you have, right? The images that you want to take. You can take pictures of yourself, right? You can take the face. It's not a convex object, but it's almost a convex object. So it works actually pretty well for faces too. So you can just put a light source at 4 or 5 different positions, right? Just one light source pointing at you or in a way that it illuminates your face nicely. And you take pictures of yourself, you know, like 5, 6 selfies, or you ask someone to take pictures of you. And then you just apply the algorithm, right? And the algorithm is linear least squares. I mean, it doesn't get any better than this, right? So all you need to do is take the images. So seriously, this is the algorithm. You take first the images. So you're going to end up with image 1, say through image n. Right? So you take n images of an object under different illuminations, of course. And now remember that what we do is, if we have an image like this, what do? We take the pixels, right, that define this image, and we have called this, we vectorize, right, this image by taking the first pixel and writing it down in a vector as x1, the second pixel as x2, and so on up to the last pixel xp. And now remember that the typical way to do that is you first write down the elements of the first row, then the second row, the third row, and so on until the last row. But nobody's stopping you from using any other approach that you want, right? It could be columns first, it could be diagonals, it could be whatever you want, but it always has to be the same, right? You cannot change from image to image. It always has to be the same. As far as it's the same, doesn't matter, right? So if I have an image here, I'm going to, image I, I'm going to write image I transpose to represent that I have vectorized this, right? And there is a function in MATLAB that does this for you, right? It's a reshape image, right, function that just reshapes a vector from matrix to vector, vector to matrix, whatever you want, right, to any tensors that you want to. So there's very little that you need to do. So you write them in vector form. And now once I have them in vector form, I'm going to have each of these images, each of these vectors, as a row vector of a matrix. And that's my training data, right? Let's just call it T for simplicity. My T matrix, which again, if I have 5 images of, say, myself, right? I've taken 5 frontal pictures of myself under 5 different illuminations. So, and then I resize the image into a vector. Reshape, excuse me, the image into a vector. And then I write it down as rows of this matrix, right? This is probably like 1 line of code, literally, right? Because when I define the matrix, each row, this is a for loop, right? That you can do in MATLAB without a for loop, but which every row of the matrix is that vectorized image. Okay? So that's it. That's all you need to do to define the matrix, right? This is your data. And now you have to apply linear least squares, which is the same as SVD, right? As we have done before. We've done this in structure for motion and many other places, right? So number 2, the second step is just to compute of this training data. Well, remember, I need to compute T, that matrix T, multiplied by T transpose, right? Obviously. So I'm going to do T times T transpose. I'm going to do SVD on that, right? And I'm going to ask for, because what is the, can anyone remind me? Keep forgetting these things. What's the dimensionality of the cone? 3. So how many vectors do I need, basis vectors? 3. Very good. So I only need the 3. So in MATLAB, you can specify this. Just give me the first 3, right? So I'm going to take these and these that MATLAB gives me. So again, this is just another line of code. That's it. And now I need one more line, right? Which is to compute the image, right? And how do I do this? This is given by V, right? Times D inverse. It's actually inverse 1/2, right? Or the square root of the inverse, if you prefer, right? And what else? What am I missing? Now I need to bring this back to a specific size, which is, so this defines my vector space, but now I need to multiply this by to reconstruct it as an image. Come on, you've done this in the projects or homework. By T transpose. Okay. And this we're going to call it our matrix B that we have defined. And what else do I need? I need the source vector. I'm sorry, the source, the light source vector, right? That's it. Now if I multiply this matrix B that defines the image, right, times the source, then I get the radiosity. That's it, or the image. I'm done. Literally, I'm done. I mean, this is it, 3 lines of code. Now, I'll give you a for loop to simulate that hemisphere. So remember, that if I have a surface like this, for any point on that surface, right, I can draw a hemisphere here, right? And what does this hemisphere represent? Anyone? All the possible light sources that I might have, right? All the possible directions and amplitudes or normals, norm of that vector, specifying the amount of solid angle and exitance of the source, right? For every possible illumination I can ever have. So what I really want, I want to represent this hemisphere, right? That's what I want to do. And that I can do by defining a for loop of the 2 angles. Remember that we had these 2 angles to define this hemisphere, phi and theta, right? So let's start with phi. I'm going to go from, I don't know, some phi 0 to some phi f, right? I don't know, whatever it is. Some values that you want, right? 0 to 90 or 10 to 20, whatever you want to include. You can also specify the step, right? Do I want to go at every degree, every 5 degrees? Up to you, right? Then for each of these angles, I also need to specify the theta. Theta, again, from 0 to some final value f. And now I can specify my source vector. What's my source vector equal to? Remember, we have the theta angle here, which was given by the cosine. Am I right? The cosine of theta times the sine, isn't it, of the other angle, right? That's my first value, right? Onto the projection onto the first basis vector. The second one is going to be given, anyone? The sine, very good, times the sine, right? And the final one is just the cosine, right? Am I right? That's it, right? And I'm done, right? So this generates all the possible light sources within this range that I have defined here, right? At whatever increments I want to specify. And that's it. Now, obviously, what I can do, I can now create my image, what's called my radiosity, right? The radiosity B, which is nothing else than my matrix B times S, right? Correct? That defines my radiosity. You all agree? Yeah? What's that?
Max.
Max, very good. So I actually need to compute the max of this or 0, right? Because it could be 0, right? If I don't see that point, obviously it cannot be negative. I cannot have a negative radiosity. That would be silly. So it's either this or 0. And that's it. That's a radiosity, right? So if you want to now image this, right, you need to create a vector. Let's call it x. And that vector, you need to reshape now the vector into the size of the image, right? Into a matrix again. So you do that. And now you can image. So it's a image SC X, right? Which will visualize the image that you have generated. Now you can end both for loops. And that will generate all the images under this or between these values of the angles. And if you save each of these images, right? You save each of these images, then you can put them together and generate a video, right? And what would be the video like? It would be a video where you see that object, static object, with the light source moving around. It's pretty cool. It's a really good, really simple thing to do, right? So I know that we've done a lot of derivations, but that's what you get when you are careful and you take your time and you do all the derivations. You end up with very simple algorithms based on linear least squares that can be implemented in 5, 6, 7, 10 lines of code, right? It's amazing. All you can do with just a few lines of code. All right. Any questions?
Professor?
Yes.
For the theta and phi, is these two angles based on the position of camera, or it's just?
No. This, remember, this specifies the direction of the light source.
Oh yeah. What I'm saying is a light source is a camera, so it's based on the light source.
It's the light source, right?
So I can't just pick randomly the angles.
Well, if you pick just any angles, that's just going to be a direction of a light source. So you're going to generate an image with that light source, right? So you cannot go wrong. There's no incorrect value for the angles. I mean, obviously, 500 is not an angle, so that'll be an incorrect number. But if you stick within the correct values, there's no incorrect number, right? All of them specify a light source, all of them. You can also change the intensity of the light source, right, if you want, by changing the norm of that vector, remember, which this vector is equal to the solid angle times the accident. So if you change the accidents, obviously you change the norm of that vector, so you can change that too. You can also do this, it's pretty cool, remember, we have shown this. You can generate two images with two different light sources, so let's call it Si and Sj, right? So let me do that. You could generate an image, B1, which is equal to the max of my matrix B times Si, or 0, right? And B2, no, Si, S1. And B2, the max of B, S2, 0, okay? Where S1 and S2 are vectors computed like this with different values for these angles, right? And now once you have this, you can actually generate a new image by simply adding these two together. Remember, this is the general model that we define. And that will give you the image as seen taken with two different light sources. Yep. Now, the more light sources that you add, the more you can tell that this is a fake image, because this is not the real world. But for one light source, it looks extremely good. Now, another thing that you can do, and that used to be extremely popular, and you have this in the slides, is that people actually design these hemispheres, right? Because this hemisphere, remember, you're required to get images under different illuminations, right? And you can be really, I don't know, unprofessional about this and just put the light source at a few places. But really, if you want to do a good job, right? And the movie industry, of course, does this with amazing technology. But what you can do is actually build a dome, right? So you build a dome like this with, actually three-dimensional dome. And you place the object right here in the middle. It could be a person, right? And this dome has many light sources all around. And usually they are flash light sources, okay? A flash, it's a light source that can flash really fast, right? Can send just a burst of energy really quickly and dissipate really quickly. So the way this works is that you synchronize the camera, the taking of the picture of the camera with the flashes. And then if you go really fast, even for people, you can do this probably in a fraction of a second or a second. And then people can obviously stay still for a second. So you can take all the images of that object or that person under all these possible lighting conditions, right? And that will give you a tremendous amount of information, of data about that object, about the shape, the albedo, everything, right? And that will allow you to do reconstructions that are extremely useful for ads, the movie industry, and things like that. Used to be that even computer vision labs at universities used to build these things. It's not as typical now, but many people may still have them. Now, I put the link in Canvas to a database of faces, right, that was collected with a dome like this, right? And you have the images of these faces under a large number of illuminations. Okay. Any questions about shading models? All right. So am I to assume that everything is super clear? All right, so let's move on to our next topic. And the next topic, I want to go back to the problem of finding point correspondences between images. And specifically, I want to find point correspondences for video sequences, right? Which is a sequence of frames of the same object, where either the object moves or the camera moves. And again, remember, we're assuming that the object is rigid, okay? Okay, there are many methods to do that, but I'll talk about one that is very popular, which is called optical flow. So again, the problem of optical flow is to estimate the point correspondences. So if I have two images of the same object, all right, but either the camera or the object have moved and the object is rigid, then I have to find which pixel in the first image corresponds to another pixel in the second image. By this I mean that that pixel in the first image, say, corresponds to this three-dimensional world point, and the same pixel or the other pixel in the second image also corresponds to that three-dimensional point. Okay, that's what I want to know. And granted, some of the points will become occluded, will disappear, or will appear. Right, we'll get to all that. But in general, most of the points are going to be present in both images. If that's not the case, then that's not really an easy problem to solve. Okay. All right, so let's start with a definition. Of optical flow, of course. We call the optical flow the apparent motion of brightness patterns observed when either the camera or the scene is moving relative to the other. Patterns observed when either the camera or the object is moving relative to the other. Now, I do want to say that the algorithms that we're going to see for optical flow do work for non-rigid objects, but care needs to be taken for non-rigid objects. Okay, so it's a little bit more challenging, but it also works. But let's assume our assumption here is going to be that our objects are rigid. Okay. Now, keywords that I'm using here. Apparent and observed. Okay. This is the optical flow is what I can observe, what is apparent to me from the images that I am given. It is not the true underlying motion of the object and the camera, because that might be unobservable, right? So for example, let's assume that I'm in a dark room, I mean completely dark, devoid of any lighting, right? And I move the object, it doesn't matter because the camera doesn't see it, right? There's no optical flow. That doesn't mean that there is no motion. There is motion. It just happens that I don't see it. This is called the motion field. So the motion field is the velocity vector associated to each image point. So for example, again, this is my image plane as always, right here. And I have my pinhole, right? My pinhole right here. And I have, say, a point P in the 3D-dimensional world, capital P, right? And that point is going to move to some other location, right? So I can call it, I don't know, P0 and P1 or whatever you want to call it. And that point is moving with a velocity, according to this velocity vector, V0, okay? And after a differential of time, dt, P0 has moved to that location. And what happens in the image is that I get a perspective projection of this through the camera, right? And here I observe my image point, let's call it Pi, my vector Vi, and my new point after some differential of time, right? So Vi times the differential of time. Correct? Everyone? Okay. So for each of that, I can define these values. This is the, what's this called again? Focal length. Okay, very good. My focal length, F. And let's call this angle alpha. And maybe I'll call this Ri, that distance. And then this distance from the pinhole to here, that point, right? This is called what? Z, very good, right? Assuming that this is X, Y, and Z. Good, great. And that here is, what angle is that? Alpha, excellent. All right, we're making progress. And this here, R0, the distance. So I can compute as we have done before. Ri, it's equal to F SEC second of the angle. I can also write that 1 over F, our focal length, times Ri, it's equal to, let's see what that would be equal to R0. So it would be 1 over R0 times R0, where now I project this onto that vector right here. which is, I think we call this the K basis vector, right? The one that points toward the image plane. Okay. So this will allow us to find the relationship between V0 and Vi, right? And let's see, so I can write that 1 over FVI. That has to be equal to R0 times K times V0 minus V0K times R0 divided by R0K. Okay. And I can rewrite this as R0 cross product V0 cross product K divided by R0K squared. Great. That's V0 here. Okay. Excellent. So, again, this is the relationship between my V0 here, which is the motion field in the world, and Vi, which is going to define my optical flow. Okay? This is a geometric relationship that we've derived many times, just written in this form. Yeah? Okay. Now, V0, remember that we could write V0 as, anyone can tell me how we can write V0 as a function of R0 here? Where am I? V0 as a function of R0. It's, where is it? Yes, what's velocity? The what again? That's correct. The partial derivative with respect to t, right? Or the derivative with respect to time. Yes. Very good. And I can also write then Vi, it's dRi over dt. Yep. Good. Okay. Now we have a problem here because my object, let's say that my object is a three-dimensional sphere, right? Like this, okay? So we're done, three-dimensional sphere, let me call it what it is. S2, or if you prefer, the ball of 2 dimensions, right? Same thing in 3D space. So what happens if I have this, and now I have a light source here that moves around, right? So this is my source. And I'm going to add one more thing, which is that the albedo of this sphere for every point on S2 is constant, right? It's the same. Okay. So what's going to happen if I have a sphere with constant albedo and I move a light source around? What am I going to see in the image? I'm going to see an image of that object that doesn't change. Very good. Now, what happens if I make the light source fixed, right, static, and I rotate that ball on the, say, y-axis, right? What am I going to see in the image? Still the same, right? It's the same thing as the first one. the illumination changes with respect to each point, but because the albedo is constant, I don't see anything. So the motion field is going to be defined by the motion of each point on that sphere, but the optical flow is null, right? There's no optical flow. There's nothing visible, correct? Right? Okay. With that caveat stated, let's see how we can derive an algorithm to estimate the optical flow. And I insist, the optical flow, not the motion field. Okay? All right. So we start with an image I, right? I take an image of my object. First image. And I can define the pixel of that image as xy. Okay? So I of xy specifies the xy pixel in my image. And I can also then specify the time t. So that means that the value of that pixel xy at time t. So that allows me to take pictures at different time intervals, okay? And I still have the intensity of that pixel over time. Now let's define the optical flow. What do I need to define the optical flow? I need to define the two components of that vector, right? Let me call them UV, as we usually do, right? I'm going to call the optical flow a vector given by U and V. Now U is going to have a value for each pixel in the image, xy, and the same for V, right? Whoops. So that's the optical flow, right? All right, so how are we going to create our model, our first model to compute the optical flow? What I can say is that the value of that pixel x, after I apply this motion, this velocity, u, right, for some differential of time, some amount of time, okay, comma y plus v, this one, right, times again the same differential of time, comma time plus what else? Delta t, very good. Right? This has to be approximately what? To this term, right? Very good. So what are we saying here? What's this model tell us? What are our assumptions when we work with this model? Anyone?
No change with time.
There's no change. There's a point, right, in 3D world that doesn't change brightness over time, or if it changes, it changes very little, right? Just a tiny bit, right? Which means one of two things. What could these two things be?
Theoretical. Theoretical.
No. What does it mean about the three-dimensional world? About the points I'm actually looking at. Anyone? That the change, what do you mean by change constant?
Not discrete.
I don't know what that would mean. Anyone else?
It's not moving.
What's not moving?
There is no relative movement between the camera and the object.
But it is, right? It's defined by UV. UV defined the motion. So what will happen in this case when I move the light source from here to here? Assuming that I have different, that this is now different, right, for all points, otherwise it makes no sense. What would that mean? If I move the light source, that's not going to be equal anymore, is it? If I'm illuminating this point right here from this angle, and now I move the light source here, that brightness, right, the radiosity of that point is going to change. So that equality is not going to hold. So we have to assume that the light source has not changed, or at least has not changed sufficiently, given that differential of time. Okay? That's an underlying assumption of that model. What else am I assuming? That the point after that movement is still what? It's still observable, right? Because if the object moves and the point becomes secluded or disappears on a rotation, then it's just gone, right? There's no equality anymore. There's no other pixel that represents that original point, so the equality can never hold. Right? So we can say that this model is appropriate if this is a good model or reasonable model if delta t is small, very small, right? So if I have a differential of a time, delta t, that's sufficiently small, then I can assume that the light source hasn't had much time to move, that most of the points are still visible, and so on, right? So under these assumptions, that's a reasonable model. We'll get to what do we do when that doesn't hold, obviously. All right, so how are we going to go about working with that model? What we're going to do is we're going to take the first order expansion, the first order Taylor expansion of that, and define a criterion based on this. Let's see. So if I take, again, the first order Taylor expansion, then I'm going to get the partial derivative of I with respect to x, the partial derivative times u, excuse me, plus the partial derivative with respect to y times v, plus the partial derivative with respect to t. And now I can dx, dy, I can integrate this over my whatever region I want to. And I'm just going to call this my criterion, okay? So again, Ix and Iy are the spatial partial derivative. And It here be the temporal derivative, okay? Partial derivative. So sometimes you will see this written down as the partial derivative of the image with respect to x, the partial derivative of the image with respect to y, and with respect to t, okay? They all mean one and the same, just different ways of writing things. Just a more compact way to write these things. Okay? So far, so good? Now, because I want to find a solution, right? I want to find the UV, right? So what do I really want to find here? I want to find a correspondence between this pixel and that other pixel, right? So this is pixel taken at time t, so let's say the first image, and this is the second image, right? I'm going to find this correspondence. And how am I going to find this correspondence? By finding the values of u and v, right? That's what's going to define this. So because I want to find this, right? I want to have this minus this, or the partial derivative, equal to 0, right? So I want to have this equal to 0. So my goal is to have ixu plus iyv plus it equals 0. I can rewrite this as ix iy times my vector uv equals to negative it, right? Or that's the same as uv is equal to it over ix iy negative, right? Obviously, that is my u and v, right? My solution. This is the vector I'm looking for. There's also obviously the magnitude of that vector that, as before, this is given by the norm of my vector, right? And this is going to be equal to it divided by the square root of ix squared plus iy squared. Correct? So these two are going to give me the direction of movement and the magnitude of that movement. Right? All right. So we are done, right? We just solve by this, solve using these equations. But there is a problem when you do that, that you are going to find out that there are multiple solutions, right? There are many UVs that are going to solve for this equation. That's too bad. So how can we solve this problem? Well, one way is to add what's called constraints, right? We can constrain that search. So what I'm going to do here, I'm going to call this criterion, let's call it ED. This is the criterion of my data, okay? And now I'm going to add a constraint. Let's see, let's think about constraints that we can add. To constrain the solution. So we only have one solution. And a common one is a smoothness constraint. And the smoothness constraint, what I'm going to do, I'm going to assume that the movement of the object over time is smooth, right? That the object doesn't move like this, right? I mean, is it possible that an object moves erratic like this? Yeah, but it's less likely that it moves smoothly, right? So I'm going to assume that there's a smooth transition or a smooth continuum in the motion. And if I have my UV vector, how can I define the smoothness over time? By computing what? By computing the partial derivative of those values, right? And what I can do is I can compute, say, ux. I'm going to use the same notation I used before, right? ux, it's going to be the partial derivative of u with respect to x, and so on, right? Same as we've done before, plus uy, right? And I'm going to square them. I could take the absolute value, but that's non-differentiable. So just going to square those. And I'm going to do the same thing for my v vector. So vx squared plus vy squared. And now I'm going to define this new criterion. I'm going to call it ES for the smoothness, dx, dy. You will typically see this written rather than this. You will see it written, this is over some region R, as the gradient of the vector UV, right? Same thing. And then here, we're going to add a function, let's call it rho, this function here, okay, where rho of x is equal to x squared, right, which is our famous least squares solution, right, the norm 2 solution. And we'll talk about how to change this later on, okay? So now I have two criteria, ES given by this equation here, and we have ED here also. So now I can come up with a combined criterion, which I'm going to do ED plus some constant lambda ES, right? Okay? Yeah? And what do I want to do? What do I want to do with this criterion? I want to minimize, right? Correct? All right. Typically, or originally at least, this was solved with calculus of variation. Which is a method to find the extrema of a function. And it's nothing else than gradient descent, right? It means nothing else that I'm going to compute the gradient of u. I'm going to compute the gradient of v, and I'm going to find the minimum or the maximum by equaling this to 0, for example. So this is equal to lambda ixu plus iy v plus it, and this is equal to times ix, obviously. And this is equal to lambda ixu plus iyv plus it times iy, right? And you just use gradient descent as we have used before. for nonlinear least squares and find a solution. One more thing that we need to solve is that we need to do this in the discrete, because images, last time I checked, have a lot of pixels these days, 10 million, 20 million, 30 million, but still a few million. It's not continuous, right? So these equations are continuous, so let's just come up with some discrete representation for them. This is actually easier than it sounds. It's actually trivial. Let's see how this works. So this would be for discrete images, okay? Applying the same thing, but for images. And obviously, there are many ways to do that. I'm going to give you the simplest way, and I'm going to then point out to what you can do to extend this to make it even better, right? But it's straightforward from here on. So we're going to start with defining each pixel, say the ijth pixel here, right, at the center, and its neighbors, right? And this has 8 neighbors, right? So it's very common to use 8 connectivity. Here, I'm actually going to use what's called 4 connectivity, which means that these corner pixels, I'm not going to consider them, okay? But it's trivial to extend it to 8 connectivity, even larger connectivity if you want to. So I'm going to define this as ij plus 1, ij minus 1. This is going to be I minus 1j and I plus 1j. Okay? Yes? Okay. So let's start with the smoothness criterion that I have defined right here. You see this criterion that we have defined here for the pixel ij. Okay, how are we going to go about doing this? Here's what I'm going to do. I'm going to look at the pixel here left and right, right? Because first I'm going to look at, where am I? Here. At the partial derivative of x and y of u, right? Of the vector that defines the velocity in that direction, right? The horizontal axis. So to find this, I'm going to take u at the pixel I plus 1j minus u at ij. And that square, obviously, because I'm using the true norm, plus, now I'm going to do the u at j plus 1 minus u at ij square, and that takes care of the partial with respect to y, right? So all I'm doing here, right, is I am comparing this pixel, right, with its neighbor, this one here, and I'm computing the difference, and I'm approximating this as the partial derivative with respect to x, and I'm comparing it with respect to this other one to approximate u of y, right? Then I have here and here, you see? Okay, so that would be the first term. Now the second term is exactly the same thing, but for v. So here I have v I plus 1 j minus vij square plus vij plus 1 minus vij square. Now I have added 4 terms here, so I'm going to take 1/4 as the normalizing constant. And that is a possible discrete computation of that smoothness term that I have defined here. Now let's go to the data term that I had. I have erased that, but you have this in your notes, right? That I have computed. And the data constraint can be computed as, let's call it Cij, as, what was that? That was Ix, right, times Uij plus Iy times Vij plus It square. And our error function, let's call it E. It's nothing else than the sum of I and j of Sij plus lambda Cij, right? And this is our term here, the error term in the discrete domain. Oop. Now let's find the partial derivatives of our error function that we have defined. So the partial derivative of E with respect to Uij is equal to, let's see, I had Uij minus Ui plus 1j, right? That's what I have right here, right? So you take the partial derivative, so it's going to be 2 times this plus 2 times Uij minus Uij plus 1 plus, if I'm taking the partial with respect to Uij, this is going to be equal to, sorry, where am I? Here. This is going to be equal to 0 and 0, right? So 0 plus, now to the second term here, 2 times lambda of Ix Uij plus Iy Vij plus It times Ix. And I can simplify this as 2 times Uij minus Uij bar plus 2 times lambda Ix Uij plus Iy Vij plus It times Ix, where now this is the mean, right, or the normalized value. And if I compute the partial derivative with Vij, I'm going to get exactly the same result as I have here, only that now I'm going to have V's instead of U's, right? It's exactly the same thing. So I'm going to have 2 times Vij bar plus 2 times lambda Ix Vij plus Iy Vij plus It times Iy, right? So to find the extrema, right, the minimum, the maximums for these equations, I need to equal these to 0, as always. So if I equal this to 0, and we compute the solution, this is what I'm going to get. Let's see that. I'm going to get the values. Again, this equaling these two equations to 0 and solving for the system of equations. And I get that Uij is equal to Uij bar minus Ix Uij plus Iy Vij plus It 1 plus lambda Ix squared plus Iy squared times Ix. And for Vij, I'm going to get exactly the same thing, but for Vij's. So it is exactly going to be, this is going to be obviously Iy, because this with respect to V. Says Ix, oops, V. Oh no, this is correct. Uij plus Iy Vij plus It 1 plus lambda Ix square Iy square. Okay. All right, so because remember I'm using non-linear least squares, what am I going to do next? I'm going to assign this as the values at time t, right? So, well, I've already used t, let's say n. So I'm going to add n here to all my values, right? To my Uij's. So, and Vij's here. So these are the values of Uij's and Vij's at time t, or n. And this is going to be at n plus 1, right? And I can iterate the system of equations, as we have shown before, to solve for nonlinear least squares. And that's our solution. Now, to compute the partial derivative of Ix, Iy, and It, I'm going to do exactly the same as I have done here, right? Now, instead of having a square like this, I have a tensor of that looks something like this. So just going to consider 2 pixels. So I have something like that. Let's see if I can draw this more or less. All right, that's not too bad, right? So I can say this is I plus 1, this is j plus 1, this is k plus 1, right? So this is the partial derivative with respect to x. There will be Ix. I can compute it by comparing pixels in that direction, right? Subtracting pixels in that direction. Iy, I can compute by subtracting pixels in that direction. And It in this direction. Okay? Same thing as we've done before. And I can get these estimates. Okay? Sounds good? Any questions? Yeah.
For the criteria, are you sure it's ED plus lambda times ES, but it seems different from your M?
I'm sorry, which one again?
So what does Cij means? Is ED or ES?
Cij. Oh, Cij. Yeah, we could call them Dijs if you wanted. I think. Yeah, I think that's your point, because we call this criterion ED, right? And then for some reason I call this Cij to follow the book chapter that I posted in Carmen. But if you want to call them Dijs to facilitate, but
In your arrow function just now, you write something like Sij plus lambda times Cij, but it's different from the criterion.
this is a criterion, no? I didn't use a criterion. Is that what you're saying?
Yeah.
So what did I use?
You use Sij plus lambda times Cij.
Sij plus lambda Cij. So I put lambda here instead. It doesn't matter, right? It's just scalar. Lambda, it's a parameter that determines how important one of the two is with respect to the other, right? Sometimes you will see people using this lambda Sij plus 1 minus lambda Cij, right? There are all these. Some people will consider lambda 1 will consider or will create a criterion, will define a criterion as lambda 1 Sij plus a lambda 2 Cij, right? And so on. There are no correct or incorrect solutions here. It's just different criteria that you can derive.
And ES here means the smoothness constraint, but what's the meaning of ED? I just get the meaning.
That was for data.
Okay.
Mm-hmm. That's the data that you're given. Okay. Look a little tired today. All right. How are we doing? Well, we are almost done. Let's call it a day, and we'll do there are many extensions of this that I want to, well, at least I want to cover some of them. I certainly want to cover the problem of the least square solution, right, of using norm 2. This is going to give us a lot of problems, especially for what's called point discontinuities or discontinuities, motion discontinuity, excuse me, of a point. So, or actually, let me do this. So imagine that you have an object like this, okay, that is partially occluding another object like this, okay? Okay? And now what I'm going to do, I'm going to move that object in that direction. And then what happens is these points, they're motion discontinuities because this object is moving in this one, maybe this object is moving in this other way, right? So in this region, right, the points are not going to be consistent, and the smoothness and data constraints that we have derived are not going to hold for these points. The problem with nonlinear least square solutions is that if we use this quadratic equation, then the points where my system doesn't hold, my equations don't hold, or my assumptions rather, are going to be more important, right? And remember, this is terrible. These are called outliers. This is going to bias our results tremendously. So we have to find inliers, right? And we're going to see maybe a few ways to address these things. There are two ways. One is to improve our formulation that we have given here. That's the first obvious solution. The other solution is to change that quadratic function for something else, right? And then we're going to probably, time permitting, see a couple of other extensions of optical flow that work very, very nicely and much simpler than this one. Okay? Any other questions? All right, I'll see you next time.